All right, AP Physics C. So we've already discussed a little bit about using calculus in physics. I wanted to finish these notes with you. Um, we talked about how when given a position function as a function of time, we can take the first derivative with respect to time to get our velocity function, and we can take the derivative of that to get the acceleration function. So that's what we've done in this example. Part B, at what times, if any, does the particle change direction? Well, if you think back to all the motion we've seen so far, changing direction means from going in one direction to going the opposite direction. So if you look at your velocity function, if it goes from negative values to positive or vice versa, then that's a change in direction. That's only going to occur when velocity equals 0. That's the moment at which it changes directions. So setting the velocity function equal to 0 sets us up with a quadratic equation. Our solutions are going to be negative b plus or minus b squared minus 4 times a times c, all divided by 2a. So that comes up with two solutions. It turns out that the particle should change directions at 0.10 seconds and 1.56 seconds. The next question, when is the acceleration of the object 0? That's pretty straightforward. You just set your acceleration equation equal to 0 and solve for time. The next question, for all times when the acceleration is 0, what is the velocity? Well, all that means is at this time, 0.83 seconds, what's the velocity? So we just plug that value into the velocity function. Part E, for what range of times is the acceleration less than 0? So when is acceleration negative? This is simply an inequality. We can set up the equation. My acceleration function is less than 0. Be careful, there's a little tricky thing that happens right here when I'm solving for t. Anytime you multiply or divide both sides of an inequality by a negative value, it flips the sign of the inequality. So we get the answer. T is greater than this fraction, which is equal to 0.83 seconds. So for all times after 0.83 seconds, the acceleration is negative. All right, now let's actually graph the position function associated with this example and see what that graph looks like. So we're going to graph negative 2, well, if we have a xy coordinate graph, we'll have to do negative 2x plus 10x squared minus 4x squared. Sorry, x cubed. So Desmos has a great graphing calculator. Let's check it out. If you haven't written down the notes, stop this video and fill them in before going over the rest, because you need your answers from the notes to understand this graph. Okay, the position was negative 2x, x being time here, plus 10x squared minus 4x cubed. If you're wondering how to do the squares and cubes, it's Shift 6 on your computer. All right, so here's my kind of wacky position function. We typically don't deal with times before t equals 0, so let's zoom in and focus on times with positive values. If you remember from our notes, we noticed that it switches directions at 0.1 seconds and 1.56 seconds. And we see that here. At 0.1, let me zoom in so we have 0.1 on our graph. So each little line is now 0.1. So at 0.1 seconds, you can see you go from moving in the negative direction to now moving in the positive direction. Also at 1.56 seconds, that's going to be this line here. It switches directions. Yeah, sure enough. All right, when is the acceleration of the object 0? That's kind of hard to see on this graph, but we said 0.83 seconds. So somewhere around here. And yeah, if you'll notice, it goes from an upwards facing parabola to a downwards facing parabola. There has to be some point in there where we're not speeding up or slowing down for that to occur. All right, let's move on to example 2. Oops. Example 2 might be the trickiest one on here because I'm not sure we've done that in calculus yet. Instead of giving us the position function, in example 2, we are given the acceleration function and told to determine the velocity and the position functions. So this is really similar to the example we just did, except we're kind of starting at the end instead of the beginning. So we just need to work backwards. So the question is, what is my velocity function, knowing that the derivative of that velocity function has to come out to be this? Well, we know this term is going to be a t cubed, but the constant in front of it needs to go away when you take the derivative. So we need a 1/3 t cubed. Over here, the term would just be t, because the derivative of that is 1. And then there could be plus c, some constant, because when you take the derivative of a constant, it's 0, and it wouldn't show up here. So here's what I would get for that. All right, to get the position function, we do the exact same thing. We work back again. So for this term, we know it's going to be t to the 4th power. We're going to need a 1/4 in front of all this so that when we take the derivative, it simplifies to this. So this is going to become 1/12 t to the 4th. This is going to become 1/2 t squared, because the derivative of 1/2 t squared is t. This is going to be c1t, because the derivative of that is c1. And then we'll have to add some other constant. We'll call that c2. Now, if these C1s and C2s are bothering you, typically on the physics problems, you're going to be given your initial conditions, and those will go away. So for instance, if in the instructions the problem had said the object begins at x equals 0 with no velocity. Well, begins, that means t equals 0. So if it began with no velocity, and you plug in 0 for t, then we can solve for c1. We know that c1 has to be 0. If it began with some value of velocity, then actually that's what c1 would be, our initial velocity. Same thing with position. If they tell you the initial position, you can plug in 0 for t and solve for c2, your initial position. All right, I hope you found this helpful, and I will see you in class.